board?
Oh my.
Yeah.
Nice.
I don't know if I'm gonna like it or not, but it'll be, well, I have to, it's right here. So they'll mount it right
Can
here.
you decline?
Have y'all seen, no, they wouldn't let me decline. I actually asked them, I was like, can I just keep that until I go? I'm an old relic, man, save this for, they're like, no. So it'll be like a big computer screen here. It might be better, because I can just write on it like a chalkboard. I don't know if I have to use my finger or something else, but
Why would they make you?
why did they make you wear a mask? It's good for you, right? I don't know, just new technology. Those bulbs cost, every time a bulb goes out, they're like $400. So they're pretty high, they're pretty expensive.
How much is a?
The board's expensive, the TVs are pretty cheap these days. So getting it basically a touchscreen monitor, it's not cheap, but it's cheaper than buying a bulb every 2 years, probably in the long run.
Are they just gonna split the middle of the whiteboard?
Yes. I don't know, it's not as big as this. That's another thing that's kind of iffy. It's gonna be harder for you guys to see in the back corner because I don't have this, like right now I can use all this space. But anyway, we'll figure it out. Maybe I'll just write big.
You could buy like a giant chalkboard and just put it right over the.
Beat the system.
Yeah, that would be
Yeah.
awesome.
We'll protest.
Just start teaching from that board. All right, so are there seriously no questions on anything we're doing? Nothing? All right. Okay, I'm going to walk away from that. We probably won't be talking about the strange sum stuff much anymore. Today I really want to talk about arithmetic and geometric sequences, which you know about, but I just want to do a quick reminder about everything that you know. So I really probably don't need this board. I mean this on. So arithmetic sequences. What do you know about arithmetic sequences? Arithmetic is when you add a number each time to get to the next number, and you could also add a negative, which would look like subtraction. All right, so examples of arithmetic sequences might be 2, 6, 10, 14, right? Examples of arithmetics could be something like 10, 7, 4, 1, negative 2. And on each of these sequences, they have what we call a what? What is it called, that thing that you add each time? The common difference, good. And that common difference, we use the variable d to stand for that common difference. And how do we find the common difference? Looking at each of these. Come on, some of you are waiting for somebody else to think. How do you find a common difference as you're just looking at this?
See what it added or subtracted.
Yeah, sometimes it's not as obvious how much it changes. Like for instance, how about this? Well, maybe that is obvious once you simplify it. Trying to be creative here, but my point is sometimes it might not be super obvious just eyeballing it. So what do? Like, what's the common difference here? What did you just do to get that?
Like 6 from 2 or something.
Yeah, you went that minus that, or that minus that, or that minus that. So the common difference can be found by taking any term, which we write by t, and subtract what? The term right in front of it. So you take any term, like the term in the second place, if n is 2, and subtract the term in the 2 minus 1 or first place. Right? So subtract terms like t3 minus t2 or t4 minus t3. And you can do that all day long. And you'll see here, the common difference here is not 3, it's negative 3, because 7 minus 10 or 4 minus 7. So when a sequence is ugly looking, and it's hard to tell what kind of sequence it is, that's a check that you're going to do. You're going to go, let me see if I get the same number every time when I take a term and subtract the one prior to it. Go with me? Okay, so that's arithmetic, and we have formulas for finding terms in arithmetics. Y'all remember that formula? If you think about it, it kind of makes sense. Like, for instance, to get to the second term, what do I do based on the first term? What do I do? This is 10. What do I do to get the second term? You add one common difference. What do I do if I want to get to the third term from the first term? I add what? 2 common differences. What do I do if I want to get to the 10th term, do you think, from the first term?
9.
I add 9 common differences. So if I ever want to get to the nth term from the first term, what do? I add n minus 1 common differences. And that was our formula we used, and that's a book formula. I think I have a better formula. The one I have doesn't make you dependent on T1 and 1. It lets you depend on any other term. And instead of having T1 and 1, what do you have? Tm and m. Remember that? And that way you don't have to have the first term, which sometimes you do, and most of the times you do. And when you do, I usually use it. But it doesn't mean you have to use it. You could use either of these. So those are my formulas for finding terms. Now there's also a formula for finding a sum of an arithmetic sequence. And a sum, you'd have a bunch of terms in the sequence, and maybe it goes all the way to some random term like, I don't know, let's think. Maybe it goes all the way up to that. And if I wanted to add all these together, do you remember that story I told you about Friedrich Gauss? Remember the little kid who was like in first grade and his teacher said he wanted him to add all the numbers between 1 all the way up to 100. And she was giving him this work to keep him busy so she could go, kick her feet up a little bit. Before she could even sit down, young Friedrich had added them all up and gotten 5,015. How did he do that so quickly? Because he certainly didn't take the time to add up 100 terms.
Compared to like a 100, I guess by itself, and then 99 with the 1.
So he compared, or even better, but you could, and that's probably what I would do. What he did was said, that's a 101, that's a 101, that's a 101. And if there were 100 terms, right? If there's 100 terms, I could take the number of terms and divide it by 2, and that would give me 50 pairs, right? And each pair is the same as the first added to the last, right? Because the first and the last is the same as the second to the last is the same as the third and the third to the last. So he just said, I have 50 pairs of first plus last. And that, right there, that 100, is what place that's in. Now, sometimes this is not in the, 414th place, is it? Because it was skipping numbers all along, wasn't it? So I want to know how many terms there are. That's what n is. N is the place of that. The place of the last term is what we call n. The actual term is Tn. So this doesn't stand, I would never put a 414 right there like I did 100. The only reason I put 100 right there in that example, or Friedrich did, is because not only was the last term 100, but it also happened to be in the 100th place. So that was just a coincidence. Okay, if I hadn't started with 1 and counted by ones, that would not be the case there. Are you with me on that? Like if I had started by 2s and went 2, 4, 6, 8 all the way to 100, then this would still be the 100th term, right? But it would have been in the 50th place. And that's place. And the place that that last term is in, if you have all the terms, also happens to be how many terms. So the n kind of has a dual purpose. It counts what place each term is in, right? N equals 1, n equals 2, n equals 3, n equals 4. But it also counts for how many terms, because the place of the last one is the same as how many. Does that make sense? Okay, so this is how I would find the sum. And can I find the sum if it's infinite? Not on an arithmetic. I can on a geometric. We talked about that a little bit yesterday. We talked about it a little bit more today. It's certain geometrics I can. But arithmetics, I can't, which makes sense, doesn't it? Because if I keep adding, it's continuing to change. And it's continuing to grow by a certain amount. It's different like on a geometric, and I think I used this example last year, like if I walked half the distance of this room, and then I walked another half the distance of the room, and then another half the distance of the room. I'm walking like 20 feet. We'll use something nice. Say it was 32 feet long. I'm walking like 16 feet, and then 8, and then 4, and then 2, and then 1, and then a half, and then a fourth, and then an 8th, and then a 16th, right? So those kind of geometrics, it looks like I'm never going to hit the wall. But I will hit it eventually, but only if I go forever. Which is hard to wrap your brain around because we don't deal in forever. There's nothing in our lives that are forever. I mean, we can say things like, yes, you know, if I travel in outer space, I can go forever. But we don't really experience that. Or the number of stars in the sky. It's infinite. But, you know, if we sat out there, we could probably actually count the ones we can see. Or the grains on the seashore, you know, grains of sand. Infinite. You know, if you had enough time and you froze the ocean so it wasn't continuing to split up granules into smaller pieces, you could count them. You'd die before you finished, which again emphasizes our finite life that we live in and our world we live in. But the whole idea of infinity, you would get to the door if you went forever. You just can't go forever, so that's a problem. But we can prove it mathematically, but those are geometric sequences, right? Because what I'm adding is half of what I did before. I'm not adding the same amount, right? If I walk 8 feet, 8 feet, 8 feet, 8 feet, I'm blowing through that door, going across the hall, and running out the English pod window out into the front. You know, so I would continue on forever. Those kind of things I can't add. Those are arithmetics. So I can't add infinite arithmetics, but I can add finite arithmetics that have a beginning and an ending, and I do it with that formula. Are you with me? Now, if I asked you to add this right here, 2, 6, 10, 14, it's easy to see the last term and the first term. But what would you do if I don't know the place of that term?
Use M and N. Like
I'd have to go use one of these, right? I'd have to pull out some other formula that helped me find n, right? So if I go to the sum formula, sometimes I'm going to be missing the place. I don't know the place. And again, don't use the term for the place. Use the terms for the terms. I just don't know what place that term is in right here. So I would have to turn around, come over here. But look, that's okay, because I know the first term again. I know the last term. I know the place of the first term is, right there, is 1. And I know the common difference is +4. I would just be missing that one variable here. So I could solve for n here and then come back and plug it in. Y'all seeing that? Or what if I said this? All right, I want you to add, in this arithmetic sequence, the first 200 terms. Right? It's not saying add to 200. It's saying the 200th term. Do you know what the 200th term is? I don't off the top of my head, but I tell you what, when I look at this, I can plug in 2 there, and I could plug in 200 there. This time, what am I missing? The actual last term, or the 200th term. Could I find that though? How? Again, go back to that formula, because look, I don't know the 200th term, but I know the first term, and I know it's in the 200th place, and the common difference is 4. So when you use this formula, almost always, you're going to need to find something else with one of these equations. That's when you're dealing with the sum. Okay? When I'm not dealing with the sum and I'm just talking about certain terms, like if I want to know the 200th term, come down here and plug it in. Right? So like right here, since I need to know that either way, I would say the 200th term in this sequence would be the first term plus, what's the place of that? 200. What's the place of the 2? 1. Common difference? 4. And before you say 199 times 4, which I'm not super great at doing on my head, think about 800 minus 4. Are you with me? To me, that's a little easier if you just apply that distributive property. So and now that I have that 200th term, it's going to make it easier to plug in there. Are y'all seeing that? And again, back to what I had before, if you don't know, if you know the last term, what did we say, it was 414? If you know the last term, then you would come in here and say, well, this time, I know the actual term. I know the first term. I know that is in the first place, but I don't know what place that's in. But I do know the common difference is 4. And if I want to distribute it, I can, or I can subtract 2, divide by 4, and add 1. And now I know what place. And then I can plug that in there. But make sure you can manipulate these and make sure you get the right common difference in there. And really, this is the kind of stuff that you're going to see, except sometimes they'll throw a sigma notation in there. What if I say, what if I were to give you that? Can you tell me right now that you know that that's arithmetic before you even start seeing what the sequence looks like? Why is that? How can you tell?
No exponent?
You're right about arithmetics not having exponents, but there are lots of stuff that don't have exponents that wouldn't be arithmetic.
You're multiplying by a constant, so it's like adding the same amount every time.
So he's right. I am multiplying by a constant, right? Which makes that like what? What kind of graph is this? If you were to graph, it's linear. It looks linear. That's like a slope, right? When you're looking at points, you're rising the same amount each time you run one term. So I'm rising 4 as I go from T1 to T2. I'm rising another 4 as I go from T2 to T3. Are you with me? So it's a linear expression. It's like an mx plus b, 4x minus 2. So if it looks linear right there, and you don't see any powers or any exponents or whatever, then you can have confidence that it's linear. But if you still don't know that, plug in a few and see. So if I plug a 1 in there, if I plug a 2 in there, if I plug a 3 in there, all of a sudden I see this same sequence start showing up. And then right there I know it's arithmetic, but this sigma means what? The sum of. So if I'm trying to sum them, I need to go, oh, I need to pull out an arithmetic sum formula. So that's where I go and say, all right, I know the arithmetic sum formula. So I need to know how many terms do I have? I have 104 terms because I start with a 1, right? We'll talk about that in a second. So I'd say I have 104 terms, right? So the sum of the 104 terms would be 104 over 2. So like Friedrich, I've got 52 pairs, right? And what is each pair the same as? When you grouped, remember what was each pair the same as? First plus the last. So I plug in the first and the last term. Do you know the first term? Yeah, 2. Do you know the last term yet?
Not yet.
Can you find it?
Yeah.
Yeah, it's whatever it's in that place, right? So plug a 104 in there and I get 416 minus 2. There's your 414. And there's your sum as soon as you do the math on it. And I'd probably try to make my life a little easier. That's a 416 divided by a 2 is a 208. And at some point, yeah, you might have to pull your calculator out and multiply that together. Right? And if you do, sorry. It's not terrible though, is it? And 832. So 21632, I think. Anyway. But I might even let you use your calculator and say set it all up. So your setup, I would need to be able to see this formula that you'd set it up and then you could just type in your calculator. So I've done that in the past too, to just make your life a little less about multiplying, a little bit more about sequences and series. Are y'all seeing this? And then what would happen if I said to go from the 10th term through the 104th? Now the first term isn't plugging a 1 in, is it? What is the first term now? And I call it the first term. It's the first term in your summation, but it's the 10th term is based on the way I'm looking at it. But when I plug a 10 in there, what do I get? Right, 40 minus 2? And then what would the next term be? 42 and then a 46. Does that change this? Do you still have 104 terms?
No.
How many do you have? 95. Why? A lot of people think I just subtract 10, but I actually wanted the 10th term, didn't I? Which ones did I want to leave off here? The first 9? So I'm going to take that 104 and subtract the ones I don't want, which is 1 through 9. I want 10, don't I? So get rid of 9, so that minus 9 gives me 95. So I put a 95 in there. My last term is still the 414, but now what is the first term in my sequence? It's actually the T10, isn't it? Are y'all seeing that? Because I'm not just blindly going through a formula, I'm actually looking at this. So I'm taking the first one in this, the last one in this, how many are in this, and this can help me do that. But remember, it's whatever my sequence starts, my series starts with that place. Are y'all seeing that? These things aren't really brutal, but they seem to be tricky on a test. I don't know if it's because you don't have tons of practice with them or whatever, I don't know. But anyway, you've got to be able to think through these and not just get so locked into your formula that you plug a 1 in there to find T1. Because that's not your first term. Are you with me? It'd probably be better to call it initial term plus final term and then number of terms and not get locked into first term and last term. But we're using that formula to help us. You with me? Any questions on arithmetic? What kind of a graph is an arithmetic sequence linked to? Linear. So when you see linear, you know that, all right, I can find a sum of finite terms. Could you find this sum? You can't. Can't do it on an arithmetic, and you can only do it on a couple or a sum geometrics, certain geometrics. And then you can do it on lots of the weird ones we talk about just because they show up at math tournaments or whatever. Which I think they're going to try to have that, what did I end up having here? I don't even remember. 104? Okay. I think they're going to try to do that state tournament, but they're going to do it at our school. Not everybody's going to come here, but like you guys will come here on a Saturday morning, take it, and go. Maybe I'll buy like donuts and chocolate milk or something.
Yes.
Because I got a really big fund since we didn't have a...
Math team rager?
Oh, wait a minute, y'all
Please throw them
y'all never been to my house, have you? That's right, because everything got canceled. I normally have like a big banquet at the end of the year. I call it the banquet. It's just like the giant, greatest backyard feast in the history of feasts. I normally drop like $1,200 on it. So like it's a
Can we get like
in the words of what was his name?
So this one will be 2,400.
No, you can't eat that much. Like I usually, I had two years ago, I had two because I had too many students to get in my house. I didn't want to bring 110 people at my house at once. So I had two like 55-ish people. It's a lot of work, but I don't see it happening this year, but there's a chance maybe next year. But you never know, maybe if this virus rolls out and everybody's like magically cured. Not the virus rolls out, but the vaccine rolls out. But anyway, no, we have like I bring in like Jim and Nick's ribs and hot wings and those cheese biscuits, and then we have like grilled chicken, and we have hamburger dogs, which if you haven't had a hamburger dog's like hamburger, hot dog or Kaneka sausage, rotel, cheese dip, bacon, jalapenos, chili. It's like the biggest thing you've ever eaten in your life, and it's truly awesome.
It's amazing.
We have those, what else? I mean, anything else you can think of. Then we have like giant fruit salads, Greek salads. And then I usually have you guys bring desserts, but I don't know why I'm telling you this because you're like, but I get nothing. But anyway, I got a lot of money from making these t-shirts and running that coffee bar. It's like, I think my balance is like $2,600. So I can certainly buy some donuts on our math team there.
Turn some mad profit.
Eating contest.
Actually, I don't make much off the coffee bar. I usually make about $200-300 a year, which is not even worth the effort, but I do it just because it's fun when they won't let me open it right now. But too much touching and exchanging of germs. But the t-shirts we make, we usually make a little money off those. Did y'all ever have a t-shirt?
Yes.
Which one did y'all have?
One
Oh, y'all had the track and field thing, didn't you? Yeah. I didn't know what I thought about that.
The
The
Murray
vision was
numbers.
great, and then it came out, I was like, whatever. We might go back to a recycled one. We'll see. Anyway, if we can pull one off. I had one for last year and then it got canceled.
What was it?
I'll have to dig it up and show. I have to find something about math, nerd, unity, and power or something like that. It's a logo I pulled from some Patagonia shirt that they had. Anyway, whatever. All right, so that's arithmetic. So geometric sequences, a lot of it's similar except the formulas, but the thinking is the same. Okay? So geometric formulas, the big deal is what?
Multiply.
You are multiplying by something each and every time. And it's the same thing each and every time. So times 3, times 3, times 3, right? And how can you determine, and then we call that the common what? Common ratio. Why would it be called a ratio? Because you find it by doing what? Making a ratio of two terms instead of a difference of two terms. So the ratio would be like the second term over the first term, or the third term over the second term, or anything like that. We write Tn, or you could write Tn over Tn minus 1, which would be any term divided by the term right before it. And it would have to be the same on each and every situation. So 6 over 2, or 18 over 6, or 54 over 18. If it changes, if this is 3, and this is 3, and this is 2, well, it's just not geometric. It might be something else, but it might be just random numbers. Okay? I mean, remember, sequences don't have to have a pattern. Like, I could write down all the temperatures of the month of October. And there's certainly no pattern, or November, whatever. There is no pattern to that, right? But I could say, hey, the first term would be the temperature on the first, or high temperature. The second term, high temperature on the second. And they would just be randomly moving all over the place. I mean, maybe over the course of a year you might see a pattern. I think you'd see more of like a sine curve, right? Because the temperatures are going to rise in the hotter months and then fall in the lower months, and then rise in the hotter months. It's not going to be perfect because it's, I mean, today the high is like 61. 2 days ago it was like 80. You know, in a week or now it'll be like the high is 37 because it's Alabama and it's just chaos on our weather. But the point is, they would have maybe some pattern, but not really enough to call it something. But this, if it's geometric, it will always have this between any two consecutive terms. You with me? And if you think about it, finding a formula, it's very simple, similar to starting with the first term and adding a common difference every time, except we don't do that. What do? When you add a bunch of common differences, plus, 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 right? When you add those, you end up with a number of common differences. But when you multiply by ratios, times r, times r, times r, times r, you end up with what? Not 4 r's, but r to the 4th, stuff like that. So the big difference is, instead of saying I'm adding n minus 1 d's, I'm going to multiply by n minus 1 r's. So it's the same kind of idea when you're looking at these terms. And that is a formula for finding what? The actual term you're looking for. But I could use that formula for finding the ratio if I wanted. I could use this formula for finding what place I'm in. I could use it for finding the first term if I didn't have it, as long as I had the other stuff. Right? I just happen to have it solved for that, for Tn, because it's the most common use of it. All right? But that's a book formula and requires you to know what? The first term and the place being the first place. But what if you had some other term like the mth term? You could still use this formula, but instead of going T1 and a minus 1, you're going to go Tm and a minus m. And that's a much better formula, I think. Although I got to be honest again, if I have the first term, I'm going to use the first term because it's easier, right? So anyway, and it's a smaller number, and I can write less often times. So in something like this, what if I said, hey, find the 10th term? What would I do with this formula? I'd say the term in the 10th place is the first term times the ratio, which is 3 to the what power? 10 minus 1, or 9th power. And then those get to be really big numbers. Do you remember 3 to the 8th?
65, 61.
65, 61. So this would be a 60, if you were doing it in your head, I would do 65, 61 is a 3 to the 8th, but you have an extra 3 and an extra 2 left over, right? So multiply that by 6 if you were doing it in your head. If you're not doing it in your head, just type in 2 times 3 is 9. But use what you have, right? That's why we memorized all those powers and then subsequently forgot them back every now and then. But if you happen to know them, use them, right? And you end up with, I don't know, 39, what? 66? Maybe, I don't know, maybe I'm right.
That's less.
Are y'all with me?
That's less than
That's
what you
less.
started with.
Yeah, that doesn't make sense.
Current
Do the magic of mathematics. 6, 36, 33, oh, there's a 3, I forgot, yeah. Yeah, the ever important whole place holding 3.
Whoop.
So anyway, make sure you can find a term, but on the flip side, sometimes I don't give you that. Sometimes I give you 39,366, and I say, hey, how many terms do you have? And you're gonna have to show me the math. You can't just take your calculator out, if you had your calculator, and go, times 3, times 3, times 3, oh, there were, 10 terms or 9 terms. You can't do that. So you're gonna have to tell me how to find it to show that setup. So how would you show the setup? I mean, I've got this formula. I know it's geometric. Can I use this? Can I use this formula to find? I know the term is that, but what place is it in? Because the place of that is also the what? The place of the last term tells me how many terms I have. So I can find out how many terms I have by finding the place of that. So what would you plug in here? 39,366? 2? 3? Now how would you solve that? Divide by 2? Now technically this is a log problem at this point. If you have an exponential equation, you can log both sides of the base of 3. What if you don't have a calculator? But if you did, absolutely. Let me ask you this. What do you know about n's values? What do they have to be? Why? You can't have like a half a place. N is a place, right? Hey, line up and somebody getting a 3.5 place. Doesn't even make sense. So if you know that this has to be, there has to be some power, which means this has to be a what? I think you're getting there, some power, but it has to be a power of 3. You just don't know them that high. You know 3 to the 8th is 65, 61. Guess what 3 to the 9th is? Now I can probably think through that if I go, wait a minute, if I just multiply by another 3. So that's 3 to the 9th. And if that's 3 to the 9th, then you really don't need a logarithm, do you? You can go, oh, I could log both base 3 and those would cancel, or I could use that 1-to-1 rule. So this turns out this is in the 10th place. Now what if I want to sum these? Now there were 2 sum formulas I taught you. You're going to have to memorize these. I can show you the proof, and I show people every year, and I showed you last year. Who remembers it? Exactly. So it's not like the proof is really helping you a lot. Anybody remember the proof? You kind of used it yesterday when we did that second strange sum problem. But anyway, it doesn't matter. The point is there are some sum formulas. There's 2 versions. Anybody remember it? Anybody? You take the first term and you multiply by 1 minus r to the n. Does that remotely look familiar? That's the first formula. And to know the sum, you would need to know what? T1, R, and N, which is great. But sometimes I don't know all of that, which means I'd have to go back to this formula and find it. But you could, if you think about it, what would happen if I distributed this in? And then what would happen if I went back to this formula and said, wait a minute, t to the n, that's the same thing as r to the n times r to the negative 1. Isn't it? Are you tracking with me? Because like basis, I would add exponents. Everybody with me? And r to the negative 1 is the same thing as what? Divided by r, or r on the bottom. And if I multiply both sides by an r, don't I, and you don't have to remember how to do this, but don't I get this? Which means these two things are equal? Well, then can I replace that t1 r to the n with r tn? That's what this gives me. So if I replace it with r tn or tnr, I've got another sum formula. But this formula doesn't use t1 r and n. What does it use? t1 r and tn. Now I don't care which one you know, but if you only know one of them, this is the one they give you in your book. If you only know this one, then when I give you a problem like this, what do you have to find? You know T1, you know the ratio is 3, but you don't know how many terms there are. So what does that force you to do? Come in here and plug it in this formula right here and actually figure out what n is. But not in this formula. If you have this formula, you take T1, bam. Ratio, bam, bam. Last term, bam, and you just plug and chug and you're done. And if you're wondering why we don't have one of those for arithmetics, you could, but it's just not worthy. It's too messy and it doesn't look pretty. And arithmetics aren't as ugly to deal with. But going through a logarithm or guessing powers, that's a little harder. So sometimes people like a bailout and that's your answer. So this is for finding sums. And this the great part is, you rarely have to go back to the other formula if you know both of these. But you're going to have to know these guys. I'm not going to give them to you like I did on that trig test where I gave you a formula page. You're going to have to know them. If you don't know them, it's going to be a massacre. Okay? Nobody likes a massacre. I certainly don't like it. It makes it really hard to grade. I like it when all y'all kill the test and it's just really easy to grade them. I get done in an hour. It's awesome. You with me? And you can also see these sums, but not written like this. You would see them written like this. How about... What about that? How do you know that that's geometric? Because I'm multiplying by something a whole bunch of times. The same thing. I'm multiplying by 3 a bunch of times. And it looks like an exponential equation. If this is an exponential equation, and it has that base form, right? You have a base of an exponential function. You have a base of an exponential function. And guess what the base is? Just like the slope was your common difference, what you were adding every time, what you're multiplying by a bunch of times is your common ratio. So you can actually look at this and see it. Now, if you look at exponential and you go, oh, common ratio is 3, that's great, but if you don't, that's okay. What would happen if I plug a 4 in? Actually, let's put that back in. If I plug a 4 in there, what do I get? 4 minus 4 is 0, 3 to the 0 is 1 times 2 is 2. There's my first term. Plug a 5 in. 5 minus 4 is 1. 3 to the 1 is 3. 3 times 2 is 6. What do you start seeing? Same thing I have here in this case. And did I have to start with a 4 and go to a 12? No. I could have started with a lot of different things. And then, but if I see this, the great thing is on arithmetics, I had to find that last term, didn't I? Not here. What do I know? T1. Ratio's 3. What else? How many terms do I have? Not 12, but what? Tell me, how many terms do I have? Why 9? Because I'm going through the 12th, but I'm leaving off the first 3. 12 minus 3 is 9. With those 3 pieces of information, can you find the sum of this, even if you don't know the last term? Looks like it. With T1, R, and N, I can plug it in there. Y'all seeing this? Let me give you a caution about your work tonight. If you are plugging junk in to find the sum, what would it mean here? If you went, okay, first term is 3, common ratio is -2, and you have 10 terms. So you plugged in your first term, your common ratio, and your number of terms. How would you simplify this? Would you do this? Oh, 2 negatives, positive. Some of y'all aren't even looking at the math. You're like, is this a trick question? What would you do? Is that true? Yes, it is. 1 minus a -2, that's a positive. Can you go right here and go plus plus? Why not? Because PEMDAS says you deal with exponents first, and what does the 10 do to that negative? The 10 makes that negative positive, because it's an even number, and then you end up with a negative there, right? Does that make sense? But what would that mean if I had a 9 right here? You don't go, oh, positive, you go, oh, 9 negatives would remain negative, and then a negative would become positive. But you have to be careful about that stuff. Are y'all with me? So these are all just similar kinds of stuff. You're going to have everything thrown at you tonight. We're pretty much out of time. But do these homework problems, guys. I'm not going to spend the same amount of time in class showing you tons of examples. That's on you. If you get stuck, make a list, and we'll hit them tomorrow before we get started, because every day we got something big to do in this before our test. All right?